Okay, chapter 3 is all about stoichiometry, which really starts off then with atomic masses and like how do we know that we have different isotopes of atoms. And so the big thing is that we can use what's called a mass spectrometer, and basically this is a device that we use to measure the mass of different atoms, and we can use it for molecules also. And then we find out how, what types we have and how much of those types we have. So you can see here in the picture, and I know this is a little bit small, but you can see in the bigger picture that I post, but basically we start off with atoms. So if we start off with magnesium atoms, we first go through ionization. So we turn them into ions by ripping off the electrons. Then in the mass spectrometer, it would accelerate those. Because there are slight variations in mass, some of them will deflect more than others. Okay, so we get this deflection area where we have a positive and a negative, but we'll get, again, different deflection based on the mass. And so that will then cause some of them to go forward and hit the detector and be registered, and some of them to not. We have to kind of change the polarization, so to speak, of the plates there in order to change the deflection. Okay, and so that's really how we do that, and that's how we have figured out that there are things like carbon 12 versus carbon 13 and carbon 14, and how much we have of those. And so notice here that, chemists have really set that carbon 12 as being the one that everything else then is based off of. It is determined to be exactly 12 atomic mass units, and everything else on the periodic table is set relative to that. So with the information that we get from the mass spectrometer, we can actually then basically figure out our average atomic mass. And we did this last year. And so remember, the average atomic mass, when we're talking about that, we're really talking about a weighted average, just like you would do with your grades. We will have 80% of your grade, your quarter grade, being due to summatives and 20% being due to formatives. And so we can do the same thing with our mass and weight it based on how abundant different things are. And so that abundance is going to, whichever is the most abundant, is going to kind of weigh the average of that mass closer to it. Again, we have to take an average because when we look in nature, we usually do not find just one isotope. We can certainly refine things to have just one isotope in them. That's kind of what is happening, in different parts of the world where they are maybe refining uranium in order to maybe make nuclear power plants versus nuclear weapons. They would use different isotopes of uranium for those two things. And so that's kind of something that is being monitored on a global scale. So just like we talked about last year, and you may remember that fun TED Ed video where they talked about buying salami at the grocery store, we're usually counting by mass. And so, it doesn't make sense typically to talk about the number of atoms or specifically molecules that we have, but to be able to count by mass. And again, that's why we need to be able to look at that average atomic mass. So the type of data that we get from a mass spectrometer is basically one of the two graphs that you see here. And so it can either be the relative number of atoms out of 100, okay, basically this is like a percentage, or it may just be that it's telling you, if this marking here was 20, then these other markings would tell you the relative amounts, and then you would have to turn that into a percentage. But those peaks and the height of those bars is again going to tell you the relative abundance of those. So if we're looking at this example here with neon, we can see that isotope number 20 is the most common, so we would expect our average atomic mass to be closest to 20. Same thing, now you just see it in a different representation here. Again, 91% of the atoms that we find have a mass of 20, so therefore we would expect that average to be pretty close to 20. When you actually look up the average atomic mass of neon, it is 20.18. So again, we can use that to estimate. Okay, so let's go ahead and take a look at an example. So let's say we were given this data. We are looking at a sample of natural copper. It's vaporized and injected into the mass spectrometer, and we get a graph that looks like this. So there's a couple of pieces of information. We know that we have isotope 63 and 65. And we can see from the graph the type of, or the amount of abundance that we have for each of those. Notice that it does say the mass values here in AMU. Those are more accurate mass numbers and will change the answer that we'll get. Okay? So anytime we're trying to find the average atomic mass, we want to try to use as accurate of a number as we have available to us. So again, for 63 here, this is really rounded off from 62.93, and for 65, it's rounded off from 64.93. So to find our average atomic mass, we want to take the mass and multiply it by the abundance. And so the abundance can be looked at as a percentage. In this case, because it says our relative number of atoms is a total of 100, we can think of these as the same thing, really, as the percentage. And so what I would want to do is I'm going to take my mass that I have for the first isotope, so 62.93, and I'm going to multiply that by the abundance, so 69.09. Now, last year when we talked about this, we talked about maybe changing your percentage right away into a decimal. I would recommend that. It keeps your numbers smaller. If you don't do that, you need to divide by 100 at the end. So I'm going to go ahead and right away I'm going to change this 0.09 into 0.6909, okay? And then I'm going to take my second mass, so 64.93, multiply that by the abundance. Again, I'm going to write that as a decimal instead of as a percentage, so 0.3091. I'm going to find the amounts for each of those, and then I am going to add those together. I don't divide by 2, I don't do anything like that. So when you think of average, I know in math class you think of add them up and divide by the number of things you had, but in this case when we're doing the weighted average, we have taken that into account by using that abundance. So we're going to get our two numbers here, add them together. So what I would get is 63.551291. I'm going to try to carry as many digits with me as I can until the very end. So this is where, using your calculator, maybe putting in parentheses around the numbers that you're multiplying together, and then you can say add, and to the second one is really helpful. But when I get to my final number, now is where I'm going to round off. So notice that our percentages and our mass numbers had only 4 digits in them, so I'm going to keep those first 4 digits here. So my final answer should really be 63.55, and my unit for this is going to be the unit of this mass. The mass number is given up here, so AMU. Okay, so when we're finding average atomic mass, we need to take our mass multiplied by the abundance, add them together for each of the different mass numbers that we have, and that will be your average atomic mass.